All right, so today we're taking a deep dive into some pretty cool number theory, Jacobi's four-square theorem. I think you're going to like this one.
Oh, yeah, this one is really fun.
So we've got a few resources to pull from today. We've got a Wikipedia article for some background,
Right.
a visualization from code docs,
Hmm.
and even some React code just to kind of see the theorem in action.
Yeah.
Now, you might already know, like, any number can be expressed as the sum of four squares. That's Lagrange's four-square theorem.
Right.
But what Jacobi's theorem does is it takes it a step further.
Yes, exactly. So, Jacobi's theorem doesn't just tell us that a number can be represented as the sum of four squares. It actually tells us how many different ways we can do that.
Okay, so it's not just about the possibility. It's about, like, how many possibilities are there?
Exactly. Yeah.
Now, the formula itself,
Mm-hmm.
it seems to have two branches, depending on whether the number is odd or even.
Yeah, you've got it. So for odd numbers, the formula tells us to add up all the divisors of our number and then multiply that sum by 8. So you kind of gather up all the divisors, add them together, and then multiply by 8.
Okay.
And that 8 is really important for capturing the different ways that we can arrange those squares. But for even numbers, things get a little bit different.
How so?
For even numbers, we look at 24 times the sum of only the odd divisors.
Oh, interesting.
Yeah, and this difference between odd and even kind of hints at some deeper number theory stuff related to divisibility and prime factorization, which we can maybe touch on a bit later if you're interested.
That would be mysterious.
Yeah.
Okay, let's hold off on that for now.
Okay.
But maybe we can come back to it. Now, the code docs you sent over had a really cool example with prime numbers.
Mm-hmm.
And I noticed that the formula gets really simple in that case.
Oh, absolutely. So with a prime number, its only divisors are 1 in itself. So the formula becomes really elegant. For a prime number, let's just call it P, the number of representations as a sum of 4 squares is just 8 times the quantity P plus 1.
It's pretty cool how it boils down like that.
Yeah.
Now, I also loved how code docs didn't just, give us the formula, but they gave us a visual representation of the theorem.
Yeah.
You can actually see how the number of representations increases as the numbers get bigger.
Right.
And plus, you can plug in any number, and it'll not only tell you how many representations there are, it'll actually show you like specific examples of the squares.
Yeah, I think visualizations like this are really powerful.
Yeah.
Because it, takes something that can seem really abstract and turns it into something that you can actually see and interact with.
Totally.
You can test it out with specific numbers. You can actually get a feel for how the theorem works.
Like turning the abstract into something, tangible, like you can work with it.
Yeah, exactly.
And speaking of tangible, we also have that React code that we were talking about. What I thought was really interesting is how the code basically mirrors the formula.
Mm-hmm.
Like it calculates the divisors, and then it applies the correct part of the formula, depending on if the number's odd or even.
Yeah, and it even tries to find the representations, not just count them.
Right.
But of course, as the numbers get bigger, that can get pretty hard for a computer to do.
Yeah, because you're basically trying every single possible combination.
Right, exactly.
So even though the theorem gives us this, like, elegant way to count the representations,
Yeah.
Actually finding them is,
It's a different beast.
it's a whole other challenge, yeah.
Yeah, and that raises an interesting question. If you were designing, say, like a game or a simulation, and you needed to use this kind of number representation, you'd have to think carefully about how to balance the need for efficiency with, actually finding all of the representations.
Yeah, it's a real trade-off.
It is. Yeah, it really is a trade-off. But it's also just cool how elegant the theorem is.
Right.
It's like this window into how everything's connected in number theory.
It's true. It's like, yeah, it's not just about the numbers themselves, but it's about the patterns and the relationships between them.
Exactly.
It's like uncovering some kind of like secret code within the structure of numbers.
And that's what's so cool about number theory. You find these like hidden connections between simple things like divisors and more complicated ideas about how numbers can be built.
Now, you mentioned earlier that there might be more to say about the odd and even cases of the formula.
Oh, right.
You piqued my interest there.
Yeah.
What else is going on there?
Well, the fact that the formula changes depending on whether the number is odd or even, it tells us that there's something special about the way those numbers can be expressed as sums of squares.
Yeah, okay.
And it all comes down to whether they're divisible by 2. So we're really getting into prime factorization here,
Okay.
the fundamental building blocks of numbers.
So it's not just some, like, random thing in the formula.
No, not at all.
It's actually pointing to something deeper about how numbers work.
Exactly.
Correct.
And this is just one example of how Jacobi's theorem connects to bigger concepts in number theory,
Yeah.
It's a reminder that everything in math is kind of connected.
It's all intertwined.
Yeah.
It makes me wonder, like, what other connections are we missing?
Right.
Like, what else could we figure out if we keep digging?
It's a good question.
Yeah,
That's the thing about math. There's always more to discover.
always.
So we've talked a lot about how the theorem works, but, you might be wondering,
Yeah.
why does this even matter?
Yeah, like, why should we care about representing numbers as sums of squares?
Right, exactly. It's interesting from a pure math point of view,
Right.
but aren't there any real-world applications?
Yeah, like, does it actually come up anywhere?
Oh, absolutely. For example, cryptography.
Oh, yeah.
How we keep our data safe online,
Right.
representing numbers as sums of squares is actually important in some of the algorithms that we use for encryption.
Wow. So this, like, seemingly abstract theorem
Yeah.
has implications for, like, cybersecurity.
Exactly. And it goes beyond cryptography, too.
Okay.
In physics, in engineering,
Mm-hmm.
understanding these properties of numbers and how they can be represented.
Yeah.
That's really important for modeling complex systems.
So it's not just, some theoretical curiosity.
No.
It's a tool that we can actually use.
Exactly. And that's part of the beauty of math.
Yeah.
Often what starts as pure theory ends up having, a real impact on the world.
Right.
So, we've been focusing on positive integers throughout this deep dive.
Right.
But, it makes me wonder,
Yeah.
what about negative integers?
Ooh, interesting.
Do they fit into this theorem at all?
Yeah, that's a good question.
It's something that our sources didn't really address,
Mm.
which makes it even more intriguing.
So does the theorem still hold true if we're talking about negative numbers?
Mm.
Would we need, like, a whole new formula? Or is this where the theorem breaks down?
Those are great questions.
Yeah.
And I think, I encourage our listeners to explore that a little bit.
Yeah.
Maybe you'll be the one to uncover the secrets of Jacobi's four-square theorem when it comes to negative integers.
It's like we've come to the edge of the map, but there's, like, here be dragons written on the other side.
Right. And you always want to know, like, what's past the edge?
Exactly.
I think that's part of what keeps math so interesting,
Yeah.
Every answer just leads to more questions,
That's
so we
right.
keep pushing further.
So to all our listeners out there, if you're up for a challenge,
Mm-hmm.
I say go for it. See what happens with Jacobi's theorem and negative integers.
Yeah, dive in. You never know, you might find something totally new. Maybe a new formula or a different way of thinking about it.
Maybe the theorem completely breaks down.
Could be.
Who knows?
But even if you don't, revolutionize number theory,
Right.
just the exploration itself, that's what's rewarding.
It's all about the journey, right?
Exactly.
And that's really what this whole deep dive has been about.
It is.
It's kind of sparking that curiosity,
Yeah.
that sense of wonder that makes us want to learn new things.
Whether you're, already a math whiz
Right.
or just starting out,
Yeah,
there's always something new to discover.
absolutely. So keep those minds sharp, keep asking those questions, and who knows what you might find out there.
Exactly.
Until next time, happy exploring.